All right, let's talk about waves. A lot of this should hopefully be review from that book activity that we did, but let's just make sure that everything that needed to come out of there was addressed. So, a wave is a wiggle in time and space, right? You've dealt with waves before, like the standard water wave that you think of when you hear that word. That is a perfect example of a wave, because water waves go up and down. They have that back and forth motion, but then they also travel through the water from way deep out into the ocean or a lake to the shore, okay? So all waves, regardless of the type, have that same sort of some sort of back and forth motion and then travel through a substance, okay? So some other examples that you may not know of that are also waves. Sound is a wave, right? It sends waves through the air, and that's how you hear things. Light is a wave. Radio is actually a specific type of light wave that is outside of our visible range. Water waves, all right? But all of these wiggle or move back and forth in some way, but do that while traveling through space, like the picture below. Okay? So, just some parts of a wave you want to make sure that you can label and recognize. So, the wave drawn below, the high points are called crests. The low points, so below the equilibrium line, just so that you know, this is the equilibrium line. So high points above that are crests, low points below that are troughs. The maximum distance from the equilibrium line to either a crest or this would also be a equally sized amplitude. All right, so the maximum distance from equilibrium would be measured by measuring from equilibrium line to the top of a crest or to the bottom of a trough, but starting from that center line. And then a wavelength is the distance from one point on a wave to that same point on the next wave. All right. Simple examples of this: if you start from a crest, you have to get to the next crest. If you start from a trough, you have to get to the next trough. All right. So these are examples. Or if you start at, where it crosses the equilibrium line going down to the next point where it crosses the equilibrium line going down. That would be another equally sized wavelength, okay? Thing is you just have to make sure that it's the exact same point on both parts of the wave, okay? Because if you say went from here to here, this is where the wave is going up, and then if this wave were to continue, it would be going down. So it's not the same point on the wave, so that wouldn't be a wavelength, okay? So, some other wave terms that you should already know, but these apply to waves as well. So, period, instead of being time for one cycle completes a wavelength. Because if you think about it, a cycle is one complete back and forth motion. Okay? So if we started here, we go up to the top of the crest, down to the bottom of the trough, and make our way back to the equilibrium point. And that is another term for wavelength. So, period, you can also think of it as the time to go one wavelength. Frequency is number of wavelengths per second, all right? And these still have the same units as they did when we dealt with simple harmonic motion. It's just now when we're looking at pictures and things like that, we may just look at it in a slightly different way, all right? And they still have that inverse relationship, so if you know one, you can always figure out the other. So, waves transfer energy. What I want to focus on is the fact that, sound. You hear it because there's an energy, a vibration that hits your eardrum and makes you hear it. It's not the molecules hitting your eardrum, it's the energy of the wave. So, while waves do need something to move through, they don't actually move the stuff. Okay? So they move through the object, but the object itself does not move. Okay? So another way to think about it is the only thing being transferred is energy, not the matter, the physical stuff. Okay? Because think about, if you've ever used a string phone as a kid, where you have two cups attached on a string, and then you talk to each other through the string. Does the string actually go into your ear? And you should all be saying, no, it doesn't. Okay? What ends up happening is the energy of the sound wave that the person talking creates gets transferred through the string to the other person's ear. Okay? Now, the energy of the wave comes from that vibration, that back and forth motion. All right? And every wavelength is one vibration. All right? So, waves do have a velocity, and that is dependent on what it's going through. Some molecules, the energy is able to be transferred faster, so a higher velocity. Some mediums, okay, that is another way to describe the molecules or substance that the object is going through. Some of them make it move more slowly, okay? Typically, faster means molecules are closer together. So an example of this is sound waves move at 340 meters per second in air. All right, air is a gas. The molecules are really separate, far apart from each other. If you talk underwater, it actually travels 4 times as fast. And that's because water is a liquid, so the molecules are a little closer together. All right, and then you send a vibration through a metal pole, that moves even faster because the metal pole is a solid, and therefore the molecules are even closer together. Okay? So, just keep that in mind. The velocity is, in some way, dependent on what the sound or the wave is traveling through. So let's talk about this relationship. So if you need to find velocity, you'll need to know frequency and wavelength. All right, and wavelength is represented by the Greek letter L, or lambda, all right, which is kind of like an upside down Y. So I usually, just to draw it, I draw a line, and then just make it an upside down Y. Okay, that's how I will draw lambda in class. But velocity is equal to frequency times wavelength, or F times lambda. Okay, so this is the equation we'll be using whenever we want to try to find frequency. Find velocity, or if we're given velocity, we could find frequency or wavelength. Okay? So, for the same frequency, so meaning frequency stays constant, and we're going to observe what changes may happen between wavelength and velocity. If the velocity is small, all right, you'll see lots of wavelengths because it doesn't, you can't get going as quickly. Whereas if velocity is very large, wavelength should be large. Okay? So the faster the velocity, the bigger the wavelength, because the vibration, the frequency, stays the same. Okay? And then if you remember wavelength, you could measure that crest to crest, you could measure it trough to trough, and you can see that these have 2 different wavelengths, and the larger velocity is faster. We'll do an activity together to practice with this, okay? So let's start practicing using that equation. So what is the velocity of a wave that has a wavelength of 2 meters and a frequency of 0.2 hertz? So information we know, lambda equals 2 meters, frequency equals 0.2 hertz. Our equation is velocity equals frequency times lambda. So we're going to have 2 times 0.2, which gives us 0.4. And then let's think about what the units would be. We're multiplying meters times hertz. But if you remember, a hertz is also 1 over a second. So we have meters times 1 over a second. That gives us 0.4 m times 1 would still be m meters per second. Okay, so it's still our standard usual unit for velocity. Okay? So what is the velocity of a wave with a wavelength of 3 meters and completes 5 wavelengths every second? So this one is a little bit on the trickier side. So just something to think about is, what information do we need to know? So this one, we know that wavelength is 3 meters, but before we try dealing with the 5 lengths every second, let's think about our equation. So velocity is equal to frequency times wavelength. So we need to know frequency, which means we need to know how many wavelengths are happening per second. And it tells us 5 wavelengths happen every second. So just like when we had to solve for frequency before, we always divide by time. So 5 divided by 1 gives us 5 hertz. So that means another known that we have is 5 hertz. Okay? So if we plug that in, we'll have 3 times 5, which gives us 15 meters per second. Okay? So remember, if you're given information like this, you're still going to be able to find frequency. You just got to remember, find frequency, you always divide by the time it takes. Okay, so it's the number of wavelengths you have divided by the time it takes. In this case, it was only 1 second. So let's look at a very similar problem. This was the one we just did. What is the velocity of a wave with a wavelength of 3 meters and completes 5 wavelengths every second? So this gave us 15 meters per second. Okay, now we've got what is the velocity of a wave with a wavelength of 3 meters and completes 1 wavelength in 5 seconds. So, slight difference, all right, but works out much the same way. We know that wavelength is 3 meters. We know we want to find frequency so that we can use this equation. All right, so we know that there is 1 wavelength in 5 seconds, which will be 0.2 hertz. Okay, so when we solve for that, we're going to have 0.2 times 3, which is going to give us 0.6, and our units will still be meters per second. Okay? Now, one last thing, just so that when we get to these problems eventually, just so you know how to rearrange this equation, it is a fairly easy one. But say you want to solve for frequency, you divide by wavelength. So frequency is equal to velocity over wavelength. Or say you want to solve for wavelength. You divide both sides by frequency, and wavelength equals velocity over frequency. You may want to write those down. But make sure you do the online form, and I'll see you in class.